Okay, let's continue our review for the Unit 1 exam in astronomy by talking about what temperature is. So you should have a good understanding for what energy is. So a related topic to energy is going to be the temperature of an object. So these two are related, but they're not the same thing. Now it is true that the higher the temperature of an object, the more energy it's going to have. And so it's going to be related to the kinetic energy of a molecule. So kinetic energy, E sub k, was equal to 1/2 mv squared, where m was the mass of the particle and then v is the speed of the particle. So that the faster a particle is moving, then the more energy it's going to have. Well, this is going to be proportional to the temperature. It's not, again, going to be equal to it, but it's going to be proportional to it. So in this particular case, you've got two thermometers. And so let's say that you take a thermometer and you put it into cold water. Well, the particles of water are going to be moving relatively slow, so that means that they don't have a lot of kinetic energy, so the temperature of the water is going to be relatively low. Now let's take the thermometer out and put it into hot water. Well, the molecules of the water are going to be moving faster, and so they're going to have a higher speed, so they're going to have more kinetic energy, and then they are going to give that kinetic energy to the thermometer when they hit the glass, and they'll give some of their energy to whatever fluid is inside that thermometer, and then as that fluid gets hotter, those things are going to start moving around more, and that's what's going to make the liquid rise in the thermometer, and then we can use that to measure the temperature of what that water is. So the official metric unit for temperature is actually going to be called the Kelvin. Now, the one that we normally use is going to be degrees Celsius. So let's take a look at the difference between these three, and you do need to know this for the exam. So what's the difference between Fahrenheit, Celsius, and then Kelvin? So the original temperature scale was the Fahrenheit one. And so in the Fahrenheit scale, water is going to freeze at 32 degrees Fahrenheit, and it's going to boil at 212 degrees Fahrenheit. But then along comes the metric system. And so in the metric system, things are based on the number 10. So they said, let's start over again, and let's call the freezing point of water 0, and then let's call the boiling point of water 100 on this new scale that we're going to invent, and we're going to call it the Celsius scale, or centigrade. So it's the same thing, Celsius centigrade. And so again, it's based on the number 10, so it's metric. But then they found out that you could make things colder than the freezing point of water. So then they said, how low can you go? So what is the absolute coldest something can possibly be? And they found out that it was approximately negative 273 degrees Celsius. And so they said, let's make up a new temperature scale, and let's call this 0. So they're going to call this 0 Kelvin. And then notice that they did keep parts of the Celsius scale incorporated into the Kelvin scale, because they called the freezing point of water positive 273. So up here, 273 Kelvin is going to be the freezing point of water, where it was 0 over here on the degrees Celsius scale. And then the boiling point of water, they just added 100 to it. So 273 plus 100 is going to be 373. So they incorporated parts of the old scale into the new scale. Now, what would happen at absolute zero? So since temperature is proportional to energy, if the temperature is zero, then the energy would be zero, and then that would mean the speed would be zero. So what would happen to those molecules? At absolute zero, molecules would stop moving. Okay, now for the exam, I would like for you to be able to convert from Celsius to Fahrenheit and from Fahrenheit to Celsius, and then also from Celsius to Kelvin. And so that's what these two formulas do. And then here is a word problem that you ought to be able to do. Plug numbers into that formula and then solve it for whatever temperature you're trying to get. So here's your typical temperatures in Kelvin if you want to look at it. Okay, so now we have a relationship between energy and temperature. I wonder if there's a relationship between light and temperature. Well, we already know that light has a certain energy, so it's not so far-fetched to think that temperature is going to be related to light. And so that's where this thing called a black body radiation comes from. So that when you take a material and you heat it up, so you raise its temperature, it will start to emit light, because the atoms are going to start to vibrate, and then as those atoms are vibrating, they're made of electrical particles, and so as those electrical particles are vibrating, they are accelerating, and we said that accelerating electric charges makes light. So the point is, when you take matter and you heat it up, it will start to glow. It will start to give off light. An example of this is your stovetop. As you make your stovetop hotter and hotter, it starts to give off visible light. Well, it's actually giving off more than just visible light. It's actually giving off all of the different parts of the electromagnetic spectrum. So it gives off some radio waves, infrared, visible light, ultraviolet. So it's giving off all of those different parts, but different amounts. So I want you on the exam to be able to draw a black body spectrum. Going up and down is going to be the brightness of the object. Going sideways is going to be the wavelength of the light that's being emitted. So on this side over here, this is where the radio waves are going to be. And then on this side over here, this is where the gamma rays are going to be. And a black body spectrum does this. So it's going to make a curve like that, which means that there's going to be a particular wavelength, this one right here, at which it has its maximum brightness. So we're going to call this thing lambda maximum. So that's the color of light that is going to be the brightest in the spectrum. Now notice it's also giving off some radio waves, but not as bright. So you notice it's not as tall over here, and you can see it might even be giving off some gamma rays, but again, not much, if any. So it gives off all of these different kinds of light, but it's always going to give off one kind of light the most, and so that's going to be lambda maximum. Okay, so how does the color, and now when I say the word color, how does the wavelength change as you change the temperature of the object? So if it's a stovetop, as we increase the temperature, what happens to the color of the light? What happens to the wavelength of the light? That's given by this formula, which you should be able to use on the test. And notice that it's inversely proportional. As the t gets bigger, the lambda gets smaller. So that's very important. As t gets bigger, lambda gets smaller. And so that the large wavelengths were over here, and the small wavelengths were over here. So if we were, let's say that this corresponds to a particular temperature. If we increase the temperature, the shape is going to change. So the shape of the curve is going to look more like that. So do you notice that the maximum wavelength was here, but now it's over here? It has shifted in this direction towards the smaller wavelengths. So here is a mathematical problem that you should be able to do. So if I give you the temperature, you can put it into this formula and solve it for the wavelength. If I give you the wavelength, you should be able to put it into that formula and solve it for the temperature. So you got to be able to do it either way on the exam. Okay, but what about the height of the curve? So the height of the curve is going to be predicted by this formula here. So that's going to be, notice it is proportional to the temperature, so that if you increase the temperature, you increase the brightness. Notice this curve is taller than this curve here. So as I increase the temperature, it got taller. So the brightness will increase if you increase the temperature, but it's not what you expect. Because you might have been thinking if I double the temperature, I double the brightness, but it doesn't. Because look at what you have to do to that T. You got to raise it to the 4th power. So if you double the temperature, it would be 2 times 2 times 2 times 2, which is going to be 64. So it's going to be 64 times brighter if you double the temperature. Now you also notice that there's another constant of proportionality in front, and so it's this thing here, which kind of looks like a 0, but it's a funny looking 0, and it's called sigma, and so it's called the Stefan-Boltzmann constant. Don't worry about it. It's not going to be on the exam, but it's another one of those constants of proportionality. And so here is the kind of thing that you should be able to do on the exam. Okay. And then we have this picture here, which shows the calculated black bodies for both the sun and the earth, and then those calculated ones are the ones that are in black. Then they actually measured the black body spectrums of the sun and the earth, and then they got that red and that green and that yellow stuff. And so all this is trying to show you is that our mathematical calculations of the black bodies closely match what really happens in nature, but not quite. All right, so having said that, don't worry about this thing being on the exam. So that concludes this particular lesson, and so we still got 2 more lessons left to go to review for your Unit 1 exam. So I'll see you for the next one.